We continue with some of our electric fields of important objects that we run into a lot. Today it's going to be the sphere and something called a capacitor. A field due to a sphere of charge. As mentioned under Coulomb's law, this is the same as the Newtonian shell theorems. Outside the sphere, it has a field as if all the charge were concentrated at a point in the center, but inside the sphere, only the charge holds closer to the center. Alright, only the stuff closer to the center counts. So if we sort of think about, we have some collection of charge, and it fills some sphere, and the key thing is that it's spherically symmetric, meaning that the density depends only on the radius but not on the latitude or longitude that you are on the sphere. It's okay that it's not constant as long as it depends only on your distance from the center. Then in case 1, we are outside and we have distance r, and we have r greater than the radius of the sphere, which we'll call lowercase r. We'll call capital R, sorry. Then if our total charge were Q, then the electric field is 1 over 4 pi epsilon naught Q over R square, and that's easy enough. If, on the other hand, we have the case where we're inside, then the only charge that matters is what's closer to the center than we are. And we would have something like when R is less than capital R, then the electric field is 1 over 4 pi epsilon naught Q enclosed. So let's do that in different color. Q enclosed over R squared. We'd have to figure out how much charge is enclosed. If it turns out that the thing is of uniform density, then the charge density would be the total charge over the volume, which is 4/3 pi r cubed, big R in that case, has to equal our enclosed charge over its volume, which is 4/3 pi little r cubed. And that tells us that the enclosed charge, in that case, the 4/3 pi would cancel, and we would have the original charge times the ratio of the where we are compared to the actual radius of the sphere, but cubed. Remember that this is for uniform density, a special case of that. Alright, for example, find the electric field at the surface of a sphere of charge of radius r, where the charge density is some initial density times the fraction of the distance we are from the center. So notice that means there's almost no charge at the center and a lot of charge really near the surface. The total charge has to obey that the charge is the integral of the density times the volume. The volume element is 4 pi r squared dr. That's the area of a sphere of radius r as we then grow it into a space dr wide. So then we can just integrate it out and say that we're going to integrate from the center to the surface of the given density function times the volume element. We play around with all the constant stuff, bring the 4 pi rho and r out. We're integrating r cubed dr. So we end up with pi rho naught r cubed. This is the enclosed charge. But then we know that now it's just a point charge, so we just take the enclosed charge divided by the distance squared, and we get something like this, so that the electric field is 1 over 4 epsilon, pi's have canceled for some reason, times the density function they give us, times the radius. The electric field grows as if we keep a constant density sphere. As we make the sphere bigger, the field at the surface gets larger, which makes sense because we're enclosing more charge. It actually turns out for this particular function that we get the field inside starts at 0 where there's no charge and grows to some amount and then falls as 1 over r squared as we expect. Notice this is the 1 over r squared that we would expect, but this is a little strange and comes out from the density function. the field gets stronger and stronger the further out we get because we're getting much more charge as we expand. All right. A really important device that we're going to talk a lot about this year, and if you go on in physics, you'll keep talking about, is something called a capacitor, which is a thing that can store charge. We form a so-called parallel plate capacitor by taking two conducting plates and putting opposite but equal charge on them. This is a device which we can use in electronics for storing and delivering charge, and therefore storing and delivering energy. So it's an important way of regulating circuits and also electrostatic stuff. Notice that by construction, we build the total charge on the capacitor to be 0, so our convention is to name the positive charge with the assumption that there is equal negative charge on the other plate. You might wonder how likely it is that you would get two plates and they'd have exactly opposite charges, but it's actually really easy to set up. In fact, it's hard to set up otherwise. So as we go on, we'll see this is a very common thing. But for now, we're just going to talk about the electric field between them. We're going to model the plates as being infinite sheets of charge. This works as long as the area of these plates is, quote, very large compared to the square of the distance between them. All right, so we're talking about plates that are pretty broad, but not separated by very much, and not tiny plates separated by, by large distances. All right, this would be no good. Remember that for infinite sheets of charge, the field points away from the sheet, at least for the positive part, and is independent of the distance. For negative sheets of charge, the field points towards the sheet, but is also independent of distance and depends only on the surface density. So separately, these would be the fields due to these two plates. All right. Now remember, these is if they were isolated, not in the system we have where they're together. But if I had just the positive sheet, it would look something like this. If I had just the negative sheet, it would look something like this. But electric fields linearly superpose, meaning we just add them to get their total effect. So we add them vectorially wherever they overlap, which means that sometimes we have the positive plate pushing away. That's what's going on here. But then the negative sheet is pulling in. And remember, these fields depend only on the strength of the surface density, size of the surface density, which is the same, right? These have the same amount of charge on the same area, so they have the same sigma, and not on the distance, meaning that these are in fact equal but opposite, and so are these, and so are these, and so are these. And likewise, here on the right, we have the positive is still pushing us away from the positive, the negative is pulling in towards the negative, but they're equal and opposite, so these are going to cancel. But in between, the positive is pushing and the negative is pulling, so these are going to add. The true field of an infinite parallel plate capacitor would be something in the middle, which does not depend on distance, and zero field outside. That's why they're so useful technologically. We generate a constant electric field where we want it and nothing outside, which is remarkably convenient actually. And it's amazing it works, and we'll talk a little bit about when it doesn't. But the electric field would be sigma over epsilon naught, because it'd be half of that for this plus half of that for that, so we get the same, and zero outside. By the way, notice how simple this has become. Because we've used epsilon naught, if we are still using the Coulomb K, then this would be something like 4 pi over K epsilon times sigma or something like that. And it would be sadly complicated. But here is nice and simple. So it's convenient that our technologically useful device has a very simple field. And that's useful. Of course, real capacitors are not infinite, because they don't have zero field and because they don't have infinite extent. So there isn't zero field outside and there isn't uniform field inside really. We get something called fringing fields, which are this bendy bit of the field here. The fact that it sort of does this and bends around at the edges. Now notice that the bigger the plates and the smaller the separation, the lesser import that we have to these fringing, right? The bigger the plates, the less they'll bend, essentially, or the less the field will make up. Notice even in between the plates, there is sort of this bowing that goes on here, also called fringing. But in the middle of our plate situation, we get more or less uniform field. And outside, we get at least weak field. Maybe not zero, but very, very weak. This is drawn from somebody's simulation. I don't know if it's a legitimate picture of a field, but it's pretty close. Also, notice that the field gets weirdly strongish over here. at the place where there's sort of the most sharp bend, and that will come out as a general principle we'll come back to. All right, 3 points inside a parallel plate capacitor are marked. Which of these things are true about the electric field? Is it true that the field at 1 is more than the field at 2 is more than the field at 3? Or is 1 the least, and then 2, and then 3, are they all the same? Or is it that 1 and 3, being equidistant from plates, are equal, but that the field is least in the middle, has minimized in the middle? And the most important thing to remember about capacitors always is the field inside the capacitor is constant. So no matter where we are, it's the same electric field.